Hello, think I'm ready. Do you see the desktop and hear me? Does everything seem okay? Let me pull up some windows.
Yes.
Okay, great, thanks. All right, so okay. Um, so where are we? Um, I wanted to start talking about data types in ML. So we're going to try to do that today. Talk a little bit about data types, which is the last chapter in the book about ML. First, the syllabus, says that there's going to be one exam for the semester, and it's going to be according to the final exam schedule. According to the university's final exam schedule, the final exam for this class, let's see, we meet on, um, we're here. So the exam's on Tuesday. Okay. So there'll be a test on ML on Tuesday. It'll be an ML test. Okay. And we haven't had a test in this class yet, but some of you have been in the operating systems class. It'll be exactly like the test was in the operating systems class. The test will be a document you download from Brightspace. You can write your answers on the document and then upload it back to Brightspace, or you could write your answers in a separate document and then upload it to Brightspace. So you'll download the exam, solve the problems, and upload them to Brightspace, and you'll have I'll give you, like I did for the operating systems class, just give you the whole day to do it so you can schedule your time accordingly. So you'll have pretty much the whole day. The exam will be available in the morning and then it'll be due in the evening. Okay, so I'll say more about it on Thursday. But the exam will be essentially, it's going to essentially be a take home homework assignment. So it's going to be a 1 day take home homework assignment. So you'll download it from Brightspace and do the work and then upload your answers back up to Brightspace. Here's all the kinds of problems we did this semester with ML. These were ML problems. So I put links to all of them. These are the ones we did in class. Now these are the problems that we also solved a lot of these in class. I'll probably put up the solutions are farther down if you go. They're all down here, but I didn't. I'll put I'll put next to these the links to the documents that had the solutions. So I had the problems in one document, and then when we worked them out as we solved them, the solutions would be in a different file. Okay, so these were the problems that ask you to rewrite these things using patterns instead of writing them the way they are. So there was a couple sets of problems where you had to rewrite things using patterns. Then there was reading type declarations. Okay, you had to annotate these functions so that they had the right types. So you would add the type information, just like in Java, you have to put types on everything. So these problems ask you to put types on everything so that they have the correct types. So it's just practice in understanding how ML figured out type. So we had these kinds of problems. So and then there was versions that were polymorphic. And then we had a bunch of examples of recursive functions. You use these for the third homework assignment. Okay, so these weren't problems. These were just the examples, good examples of the kinds of patterns you see in recursive functions. Okay, and then these were the problems where I gave you a type and you had to write a function that had that type. Okay. And again, the solutions are farther down the page. I'll probably put a link up here to where the solutions are. And then this one I haven't finished yet. I was going to put a few more problems up here of like summarize what we've been doing. So I haven't had time to write this one yet. Okay. So these are the kind of problems you have on the exam. It'll be, variety of problems like you see in these documents here. If I give you a, I'm sorry, if I give you a type, you should be able to write a function, a simple function that has that type. Okay. Or if I give you a function, ask you to annotate it with what the types are. Okay. Add the type information to the function. Okay. All right. So, and also be able to write simple recursive function. So there'll probably be a couple problems on the exam to ask you to write a couple 2 or 3 line recursive functions. Okay, so it'll be a take home, essentially some take home problems in working with ML. Okay, and look at these problems. I mean, hopefully, these are what you've been looking at during the semester. These are the problems that pretty much, I mean, ML is something you learn by doing. So you need something to work on to learn the language. It's not enough just to read about it. So these are the things you do to get a sense of how the language works. Okay. All right. So there's that. The next thing is there's a last homework assignment. It's actually due Thursday. Does anybody have any questions about this homework assignment? So like, now's a good time. If anybody's got a question they wanted to ask about, or this one, or the fourth one too, because some people are still working on the fourth one. Anybody have any question about either one of these homework assignments? Anything you want to ask at this point? Let me just open them so that they're ready. Anybody got any question about the last 2 programming assignments?
Professor, what would you consider to be just like the ultimate deadline of the class? Like if we have a late assignment?
Oh, we'll see. Now, grades are due, next week is final exam week. Oh, grades are due 2 weeks from today. So I'd say next Wednesday or Thursday, because I need time to do the grading. So 5th or 6th of May, middle of final exam week. That'll give me, it also depends a lot on how many people turn in late assignments. If a whole bunch of people turn in late assignments, I'll have trouble grading all of them on time. If most people get them in on time earlier, I can accept things later if there's not that many of them. So I'd say, the safe thing is May 5th or 6th. Okay, and that would give me 5 days to grade them, because the grades are due on the 11th.
Okay.
So say the 5th or the 6th. After that, it gets iffy. You can turn them in up until the day the grades are due, but I may not have time to look at it. So if you don't get it done until the 9th, go ahead and turn it in. I'll see it. If I have time, I'll look at it. It kind of depends at that point on luck. If there's a whole lot of people turning in stuff that late, I probably won't have time to grade all of it. But if you're the last person to turn something in and there's nothing else, everything else has been graded, I'll have time to grade it. But to be safe, I think if you get it in by the 5th, I'll have time to grade everything. Okay. And if you have questions, keep on asking questions. So if you have questions, I'm trying to get through all the emails. But if you have questions, go ahead and ask. It doesn't hurt to ask. I'm trying to answer all the emails I get. Okay. All right. So keep working on them. But okay, now what about 4 and 5? Does anybody have any specific question about 4 or 5? Anything that's come up? Anything that you want to ask about in class for 4 or 5? Anything? Okay. Oh, I added something after class here. This is kind of fun. We were doing the higher order functions using, we had all these examples, where you had to figure out what map that function on that list. We talked about these. Well, you can do these in Java if you go to this website here. This Coding Bat website has nice examples of map problems and filter problems in Java. And they have a good page that describes what you need to do. Like if you click on this here, oh, not that one. Where was it? Oh, yeah, I'm sorry, right here. Here's the link. If you click on this link here, they have a nice explanation of how to do map in Java. There's 2 versions of map in Java, one called replace all, and then one actually called map. Here's the one they called map. They do a nice example. They do a nice job here of explaining it, and then they give you problems to do, like apply the write something called doubling that takes a list and doubles everything in the list. So doubling takes a list and gives you back everything doubled in the list. So it's a simple example of a mapping. Oh, and if you click on this button here, they give you a lot more, that more or less that information that was on the other page is reproduced here. Okay. And if you read this, it's pretty well written. This, I don't even know why they made you click this button to get this. They should have just put this up here right away. But you click that button and you get this little help that describes how to do maps. There's the function that you're mapping. Notice it's very close to ML's notation. See, ML, I write fn of x goes to, and I use what people call a fat arrow. ML uses what people call the fat arrow, and Java uses what people call the skinny arrow. In some languages, you actually have both fat and skinny arrows for different reasons. Okay. Oh, and ML has fat and skinny arrows. It uses the skinny arrow for types, and it uses the fat arrow in function definitions. So it uses the fat one in the definitions and the skinny ones in the types. Okay. Do we have any types on this page? Yeah, see, skinny ones are in the types. Okay. Java uses the skinny arrow for the function. This is the input, that's the output. Okay. Okay. So that applies this function to all the numbers in that list. Okay. So that's kind of it's good. I keep saying that one of the reasons for studying ML is because the ideas in ML are filtering into all these other languages. And this is a good example where these people have created these homework exercises where you can see in Java how to do the map and filter and things like that. Okay, and here's another one. Okay. These are filter problems. So see, this list gets filtered down to a shorter list. So they're not map problems, they're filter problems. Which elements in this list make the filter function true. Okay, so it's a filter function, and this one you're supposed to filter out the negatives and leave only the positives. And we did an example like that in ML. We did something similar to that in ML. So here you just see that if you solve these problems, you'll see the Java notation for doing these. And there's two notations. There's this notation using here, and there's this notation here using what's called streams. This is using list notation, and this is using stream notation. So there's a little bit of a quirk that Java has two ways of doing these things. You can use lists or streams. ML just has lists. And Java has two ways because all this stuff was added to the language later on, and they couldn't decide what was really the right way to add it to the language. So they ended up adding it to the language two ways. Okay. Okay. So that's kind of, I think that's interesting. If you want to, especially if you're more interested in Java programming than ML programming, you should go to these and see how to use what we've been talking about in ML in the Java language, how to do higher order functions in Java. Okay. So, oh, and then here's their explanation of map, and here's their explanation of filter. Okay. Java, notice that they use the phrase functional filtering. This is where Java acts like a functional programming language. And they, all the stuff in here was directly influenced by ML. In fact, one of the persons who helped write the functional part of Java was one of the persons who helped invent ML. There's some overlap between the people who originally did ML were ended up joining some of the teams that worked on Java, and their expertise in functional programming moved into Java. So some of the same people. Okay, all right. Now let's see. Let's look at some stuff about data types. Okay, there's this fourth look of ML in the book that's about type definitions. Okay, and data types in ML are actually, I wish we had more time for this. There's two things in ML that have really influenced the world of programming a lot. One is pattern matching, and the other is ML's types. ML has what's called algebraic data types. And if you've never seen them before, and you probably haven't, they're kind of confusing. Algebraic data types are a really, see, there's a whole lot. You'll find tons about them in the internet. This is something, it's in ML that is not going to show up in Java probably anytime soon. It's too hard to add algebraic data types to Java and C++. But Java's kind of faking it. Java's got some things in it that are like really weak approximations of algebraic data types. On the other hand, anybody who invents a new language is putting these in them. So Rust has algebraic data types. Apple's Swift language has algebraic data types. The TypeScript language, which is a dialect of JavaScript, it has algebraic data types. So anybody who's inventing a new language in the last couple of years is giving those languages algebraic data types. But it's proving to be a little bit tough to put algebraic data types into Java and C++. They're trying, and I'll show you later, like maybe one or two places where Java almost kind of does what's called an algebraic data type. Algebraic data types are a little bit tricky. Okay, they're especially since it's something you've never seen before, unless you've learned a really modern language like Rust or TypeScript or Swift or one of the really newer languages. You won't have seen algebraic data types. Okay. There, let me show you a real simple example of something I wrote that has an algebraic data type in it. Okay, here's a real simple little program. Here's a data type in ML. I call it boolint. Okay, and it's one of two things. It's got a Boolean part or an integer part. So a value of this type is either a Boolean or an int. Now, this is the thing you can't do in Java at all. I'm essentially saying that I have a data type that holds, well, depending on what I put in there, it could hold either a Boolean or an int. So I could have a variable, I'll go down here, I could have a variable val x equal, okay, I'm going to say bool part true. Okay. Now what I did is I have a variable of type bool int that holds a Boolean. Okay. And here's a variable of the same type that holds the other possible Boolean. Okay. And then I could have another variable of this type that holds. Now, all these variables have the same type. The funny thing is they all have the same type. This is called a constructor for that data type. So bool part is a constructor of a boolint, and int part is a constructor of a boolint. This one constructs one of these holding a true. This one constructs one of these holding an int. Whoops. Okay. So if I go over to, I'll copy and paste that into ML. Okay. So now I have this new data type. Now, defining a new data type is a lot like defining a new class in Java. You're defining, when you define a new class in Java, we'll play around with something called a rectangle class. When you define a rectangle class in Java, you're defining a new type. You're saying, oh, I can have variables of type rectangle now. Okay, so now I have variables of type boolint. So I can go, see if I did this right. I can put these variables in there. See, now what is x? X is a boolint. See, its value is true, but it is a boolint. And W, what is it? W is a boolint, but it holds an int. So I have these variables where the variables can hold either an int or a Boolean. Okay. Now I have another kind of variable in ML. I can do something like this. I can say val a equal a tuple. Notice that a holds a bool and an int. Okay. Now, a holds a bool and an int. X holds a bool or an int. And this anding and oring of data types is the algebra of algebraic data types. Somebody had the brilliant idea that that you could form an algebra of data where you do ands and ors, and you say, well, X is a bool or an int, but Y is a bool and an int. Now, the and data types are tuples, and Java has those. Okay. In Java, when you do something simple like, here's it, public class stuff. I'm going to put int x, string, let's see, no, bool y. Okay. Okay. There's a class that holds an int and a boolean. See, there's the and. A class, when each field, an instance of this class holds one of int and one bool. So there's the and of algebraic data types. It's been there in Java, and it was there in C++. In C or in C, you would say something like struct stuff int x. Well, if it was C++, you could do bool y, but not in C. Okay. Yeah. So you can do a strut. Okay. That would be an instance of this holds an int and a bool. But there's no way to do this or thing. There's no way to create the thing that is a bool or an int. This has no analog in Java or in C or C++. Okay. Now here I wrote functions that make use of this. Like here's a function f that if x is a negative number, it returns the tuple false -1. If x is a positive number, it returns the tuple true 1. Okay, so this function can be said to return two things. It returns a Boolean and an int. Okay, so in case of Java, I could have a function that returns a stuff object. So I could write this function here. In fact, I could call this one, I could call this bool and int. Okay, so I could have a function in Java, f would be a function that returns a bool and int. Okay, but look down here, this function g, if x is negative, then it returns a bool part false. So the function is going to return one of these bool ints, but if it has a positive number, it returns an int part 1. Okay, so it returns the Boolean for negative numbers and the integer for positive numbers. Okay, so we can say that f returns a Boolean and an integer, and g returns a Boolean or an integer. And this anding and oring is the heart of these things called algebraic data types. The and part is not that deep. That was there in every language from the beginning. Somehow the and parts is very natural to put pieces of data together in a strut. So there's an int and a bool. The harder thing was to do this, of putting two things, but they have one or the other. Now, Java doesn't have anything like this. Now, C does have something like this. C has something called unions. In C, you can do a union. So this would be a Boolean, bool and int. You can also do bool or int with a union. But unions are really hard to work with, and they're nowhere near, they're not really an algebraic data type. They're not quite an algebraic data type, but they do have this sense that this thing holds either an int or a bool. Okay, but in a really weird way. C unions, what it amounts to is that way back in the 70s, The people who designed C realized that this or idea was relevant to the language. This idea that you could have either something that is a bool and an int, or you could have something that's a bool or an int. They kind of realized that that was a useful idea, and they came up with unions. And unions existed in other languages back then, but they're very messy and difficult to work with, real error prone. It didn't solve the problem real well. So union data types, these are called union data types. They're kind of they're really useful in C programming, but they don't do a very good job of capturing what people really thought was the right idea. The ML people came up with a much better way of doing these union data types. Okay, and it's, see this bar here, you read that or. See, a bool int is a bool part or int part. Notice that this vertical bar is used to mean or in lots of places in ML and in Java too. You know, a single or means bitwise or, two bars means logical or. We've used the bar in ML to define functions. When we have multiple definitions for a function with pattern matching, essentially we've used this as to say the function has one definition or it has another definition. Depending on the input, we say, oh, this function has multiple definitions. Here it's used for saying that this data type has multiple structures to it. It's got a Boolean structure or an integer structure, okay? So I can do these two functions here. Okay, f returns, takes in an int and returns a bool. You read this as and an int, a pair, a bool and an int. On the other hand, g, it returns a bool int, which if you go back to my definition, you see that a bool int is a Boolean or an int. Okay. Now, in some languages, people are actually, notice that I don't in ML write something like this. And people are trying, in some languages, you can almost do this. Notice I have this bool part of bool, and I have this int part of int. In some languages, I think TypeScript, for example, you can just say data type bool int is bool or int. Okay, you say it's a Boolean or an integer. ML doesn't use a syntax like that. And there's advantages and disadvantages to saying, whoa, bool int is a bool or an int, as opposed to saying Boolean is bool part of Boolean. So you give a name to this part, and you give a name to that part. So the names are called constructors. So the Boolean part of a bool int has got the name bool part. And I could give it any name I want. I could have called it Bob and Alice here, but normally people give them names that are kind of readable. So a bool int has a bool part and an int part. But some languages just let you say a bool int is bool or int. You know, and you can give it, then you could say something like x is a bool int and its value is 5, and y is a bool int and its value is true. I think you can do this in TypeScript. You can just, I think in TypeScript you can type it just like this, more or less. Okay. Whereas ML, you need this more elaborate thing of giving each part a name, a constructor. Okay, so then see down here, I have to say x is bool part true, y is bool part false, z is int part 5. Okay, okay. Notice that here you have to say, but it's a bool int. If you just do that, you're declaring an integer variable. See, if you just do x equals 5, that's just an integer variable. If you just do that, that's just a Boolean variable. So if you want it to be a bool int variable, you have to say in these languages, x is a bool int and I'm giving it an integer value. Y is a bool int, but I'm giving it a Boolean value. Okay, so in languages that let you just declare it like this, then you have to say what the variable type is. Now down here, I don't have to say what the variable type is because this says it for me. a bool part is part of a boolint. If I want, I can say this, but that's redundant. Okay, that's just kind of, that just says that's redundant because this part specifies that this is. Now, what I can't do, which would be nice, is that in ML. See, okay, X is a boolint. I'm giving it a Boolean, so it should put the Boolean in the right part, but this ML won't accept that notation. See, didn't like it. I have to, if it's a boolint, I have to use the constructor name. I have to say, I have to say bool part true. Okay, so if I have a variable, see, so see, now that works fine. Okay, now that makes sense. So X is a Boolean, so it's either a Boolean or an integer. So if I give it a Boolean, ML should figure out what's going on there. And I think it's just that the language was invented some many years ago, and probably they quite couldn't get it to be that elegant at that point. Actually, it's hard. I'm not sure. The constructor idea also has a lot of advantages. So making you say what part of the or you're using, whether it's this half of the or this part of the or, making you give it a name has real advantages. So when you write more complicated code, the constructor name makes things very readable sometimes in some uses. So I'm not sure if they didn't want this notation or if they couldn't figure out how to make it work. Some of the more modern languages, like I said, I think TypeScript does it this way. And I can't remember if I don't think Rust does it this way. You just say boolint is a bool or an int, and you just say X of type boolint is 5. But then you have to do that. Because if you do that, it doesn't make sense. Well, then X is just an integer variable. By default, if you just say X equals 5, then X is an int, not a boolint. Okay, so then, like, if you do this, you could later on say X equals true. And that'll make sense because X is a boolint, so it can hold either an int or a Boolean. Now, notice that that's way different than Python. In Python, you can do this. But that's because variables don't have types. There is no type to X. So sure, you can put a true in it, and later on you can put a 5 in it, and later on you can put a string in it. That's because the variables don't have a type. In this case, if you try to put a string in X, you'll get, in TypeScript, this would generate an error because X can hold bools or ints. So you could give it an int value, you could give it a Boolean value, you can give it a Boolean value, but you can't give it a string value. This would generate an error. Okay, this would be fine. This would be fine. This would be fine. This would be an error. In Python, this is fine, this is fine, and this is fine because X doesn't have a type. Okay, but you got to be a little bit careful. But you got to say that X has that type. You have to make sure that X is a bool int, so that so that the language knows it's okay to put booleans in it. It's okay to put integers in it, but it's not okay to put strings in it. Okay, so that's one reason why this stuff can get kind of confusing when you read about it on the internet, because what looks like this and this look alike, but they're very different things. This is algebraic data type using an OR. This is just no data type. Okay. Now, if I go up here and I give this guy a string part, I could give this thing a string part. Well, here in a TypeScript-like notation, I could just give this a string part. So yeah, then I could just give it a Boolean string or whatever. I could give it a string part. Then I could give it either a bool, int, or a string, but I wouldn't be able to give it a double value. That would still not work because that's not a Boolean, an integer, or a string. So this one now wouldn't work. Okay. Whereas in Python, you can put anything in anything. Okay. So, in Python and JavaScript, JavaScript, this would be like Python or JavaScript. They are untyped languages. Okay. But this would be TypeScript. TypeScript is a typed version of JavaScript, and it uses very modern typing, so it uses algebraic data types. TypeScript uses algebraic data types. JavaScript just doesn't use data types. So you can do anything with a variable X. Okay. ML, okay, all this is not ML. ML has algebraic data types, but you have to give names to the pieces. Okay. And then you can do interesting things. You could have functions that return, like I say, a function that returns a Boolean or an int. Okay. Now, let me show you why this, where people, what people start doing with this. Here's a real famous example of something that can go wrong. Okay, suppose I do string cat. Okay, well, string s equals cat. Okay, in Java, and use the Java visualizer to write some Java code. Okay, then I do int n equals index s dot index of z. Okay. Okay, what's the index of z in cat? Well, doesn't have it. There is no z in cat. So how does this thing report that it can't find the answer? Okay. So what's the, how does Java tell you it couldn't find z?
Give you -1.
Yeah, it gives you a negative number. Now, what's the point of -1? Why does it use -1 as the answer?
Because that cannot be used as an index for a string.
It couldn't be a valid answer. So it's a now like 0 is a valid answer. The index, like the index of C is 0. So the -1 is not a valid answer. Okay. Now, if you think about it, now here's okay. Now, but suppose I'm writing a bunch of code, and 1,000 lines later, I do something like the following. I say, I need the, I have this other string S2, and I need to find the char at init, the same place where the z was in string 1. So I use n. Okay. So suppose I have some string S2. Okay. Suppose I have this string S2, I have this string S1. I'm supposed to find the index of z in S1, and then find out what letter is at the same place in S2. Okay. So I find out where the z is in S1. Then I say, okay, now where is the z in S2? What's at that place in S2? So find the z in S1, then find the character at that place in S2. And the program crashes. See? Why did the program crash? It was supposed to find where the z is in S1, and then use that answer to find out what letter is at that same place in S2. This is how bugs get into real programs. This makes perfect sense, right? Find where the z is in S1, what letter is in S2 at that same place. What's wrong with the code? What's wrong with the logic? Yeah, this could fail, but the compiler has no way of denoting that. This thing could fail, but I can go ahead and use the failed answer. This is really an OR. What does this answer give you? It gives you the index of Z, or it gives you a failure. That's actually an algebraic data type. But Java doesn't have algebraic data types. So Java gives you a fake answer here, -1. Well, -1 has the right type, but it actually means failure. But if you go ahead and use it, your program can crash. This is actually how bugs get into real programs. This is a problem. This is a big problem. Java doesn't have OR data types. I can't say that this thing gives me back an integer or an error, okay? And that's what I really want to have happen here. I want this to give me back an integer or an error. And then down here, I would have to, now in ML, what'll happen is ML will tell you, well, see, N came from here. If this was an OR, there'd be two parts to the OR. And you'd have to say which part you're using. And then you have to actually make sure you choose the correct part. So you have to essentially check if there really is an integer there. You'd be forced to check. You would actually be forced to do the error checking. So what's happening here is I should do the following. If N is greater than or equal to 0, then I can do this. Else, report an error. Do something, handle the error. Okay, I really should double check that this thing could have given me back an error, that there was no Z in this string here. But the compiler has no way of forcing me to do that error checking. One of the things that algebraic data types do is in a really well-designed program using algebraic data types, if I say that index of returns an OR, it returns an integer or an error condition, then down here, I'll be forced to check if I got the integer, use it. Otherwise, I got the error condition, do something else. But since Java, since this thing returns an int, no matter whether it succeeds or fails, the compiler has no way of knowing that to force you to check your error condition. As a programmer, you learn to check the error conditions. Usually you learn that the hard way, but the compiler will compile your code. See, if I just do that, the compiler compiled the code without knowing that I have an error condition here. The compiler has no way of knowing that I really meant this thing to be an OR. Size of should have returned an int or something to denote an error. In the case of ML, we can, well, now Java does have this thing here, okay? In Java, there's something new. There's something called the optional, okay? An optional is an OR type, but a very poorly designed one. An optional either holds something or it's empty, okay? It either has a value or it's empty. Now, what I want is index of should return an optional, where it either has an integer in it or it's empty, meaning it didn't find the Z. Now, if people were rewriting the Java libraries, index of would return an optional, but they can't go back and rewrite index of because it's too late now. The optional was added to Java. Does it say here? Sometimes they'll tell you when these things were. Oh, see, it was added real recently in Java 1.8. That was about 8 or 9 years ago. So it was added in Java 1.8, which was 8 versions of Java after Java was invented. Okay. This is an example of Java trying to imitate an algebraic data type. Okay. And an optional holds two things. It holds a value or it holds empty. Okay. And functions like index of that could return a value or not return a value should return optionals. Okay. Now, another example of this is when you, in Java, if you go, if you look up the list class in Java 11, you can search a list. See if I find the oh, I thought this, let's see. Oh, yeah, index of. See, there's an index of, okay? You want to find this object in the list, and you want to know where it is, okay? And you get back -1 if it doesn't find it. This function should return not int, it should return an optional. And they're starting to rewrite now. There are some places in their library where they rewrote things to return optionals, whereas the optional would say if the optional found what you're looking for, then the optional would hold an int value. But if it didn't find what you're looking for, then the optional would be empty. It would actually be the empty value. Okay. Then if you called empty on it, it would get back true. Okay. Now, the compiler tries to enforce these things. If index of returned an optional, I couldn't just plug the optional into char at. I'd have to check if the optional actually is not empty. I'd be forced by the compiler to check if the optional is not empty. So I couldn't accidentally use an empty optional on char at. Okay, so that would help make my program a little bit more less error prone. Here, I can get back an error, essentially an error value, and use it. See, the trouble is an error value is a legitimate int, so I could use it, but my program will crash. If this thing returned an optional, I can't use an optional here. I'd have to check if the optional holds an int. So I'd have to use what was called I'd have to call the get method or the present method to find out what is in the optional. Okay, but it doesn't work very well. The optional class in Java is actually, it helps, but it still ends up not solving the problem because the optional is tacked on to the language and it's not a true algebraic data type. It's not a true OR. It's kind of it's a little bit messed up, but it's attempting to be an OR data type. Okay. And it's meant to help you catch these errors. I'm not sure if I'm trying to remember where in the language they rewrote some things to actually use optional. I think you have to go to the stream library. There, see? You're supposed to find something in a stream. You may find it or you may not find it. If you don't find it, you get an optional that's empty. See, so see here, the stream library is way newer. Well, see, the stream library was added in 1.8. So at the same time they created optional, they created the stream library. The whole stream library was created at the same time. And the stream library kind of replaces the list data type. It's a more modern list. And it does things like, instead of returning an index, when you want to find something, instead of telling you at -1 if we couldn't find it, or it gives you back optionals. And the idea is that this is trying to be an OR. The optional is either the thing you were looking for, or empty. Okay, so there's several places in here now where the modern version uses optionals. Okay, so there's several places where they're using optionals to, and the optional is always there to mean success or failure. The two parts of an optional are there's the empty part, which is usually meant to mean the function failed, and then there's the part that's not empty, which holds a t. So you could have an optional of an int, or an optional of a string, or an optional of a Boolean, and it would hold that thing or be empty. Okay, so almost all languages are trying now to move in this direction of algebraic data types. They all have the and. The interesting part is the or. The or is turning out to be, the or is the tricky part. Now, ML had the or back in the 1980s, and it's taking all this time for languages like Java to try to pick up on this or idea, that something can be this or this. Okay. Now, if you actually looked at the code for the optional type, you wouldn't see any or in it. Okay. It doesn't have, Java doesn't have the or idea. So this is written in kind of a kludgy way that tries to mimic this idea, but it doesn't do an especially good job of it. Okay. And if you read about the Java optional, you'll read tons of articles about how it's helpful, but it's better than what they used to do. It's better than returning a negative number to mean I couldn't find what you're looking for. It's better than this, but it's still not as good as the true algebraic data types that they're putting in languages like Rust and TypeScript and newer languages. When, like I said earlier, the old functional languages like ML and Haskell had this way back when, and people now, starting in the last 5 or 6 years, if people invent a new language now, they will put algebraic data types in the language. So let's see, Rust has them, Swift has them. I can't remember if Go has them. I don't think Go. I don't think they put them in Go. Go, see, right away, Go and algebraic data types. Yeah, why doesn't Go have algebraic data types? They didn't put it in Go. And part of it has because Go was designed specifically to be a little bit of a more old-fashioned language. Go was actually designed to be with a lot of, Go was designed in kind of an odd way. It wanted to kind of tread a middle ground between older languages like C and newer languages like Rust. So it chose not to have algebraic data types. And you can see that and of course, right away, people are proposing that algebraic data types be added to Go. Okay, so, but almost all the newer languages that have come out in the last few years have put the algebraic data types in them. Okay, so for example, algebraic data types are in. If you look up the stuff on advanced types, you can find see, there's the or. See, a pet is a fish or a bird. See, it's kind of, they use a lot of weird examples, but see, a pet is a fish or a bird. Okay. So there's the or that lets you say something. See, pet has type fish or bird. Okay. So there's the or of the algebraic data type. Notice that ML in TypeScript, you don't need you don't say part, you don't say, it's not as verbose. You just say this thing or this thing. Okay. So TypeScript has the algebraic data types. Rust has them. Swift, I'm pretty sure, has them. I'm trying to think of other more recent languages that have been invented lately. And Go kind of famously, there's a few other things that were modern that Go avoided. Go's a very nice language, but it was designed with it didn't try to be ultra modern. It wasn't trying to be ultra modern when it was designed. So that's an example why it didn't end up with algebraic data types. Okay. Now, ML's, let's look at, now this is the fancy part of ML, the algebraic data type where you can do an OR. That's usually not the first thing you look at when you learn ML data types. Let's go backwards and try to do something more basic in ML. Okay. Okay. Let's look at a more basic example. Now, here's a real basic example. Here's a Java program. This is a rectangle class. Okay. So a rectangle, I'm designing, this is a typical way of designing a rectangle. You have an X and a Y that are, say, the lower left-hand corner, or it could be the upper right-hand corner, or the upper left-hand corner, lower left-hand corner. You pick a corner and a width and a height. Okay. So a rectangle is 4 numbers, and then you have a constructor. Okay. And then you have methods like move the rectangle, compute the area of the rectangle, figure out if 2 rectangles are overlapping or not. Typical examples. This is from the Java course. This example came out of, this was a first example on how to describe classes in the Java, in the CS123 class. So this was defining a type. So after you define this, you can talk about rectangle objects. Okay. What about ML? How would you do this in ML? This is an and. Okay. A rectangle is an X and a Y and a width and a height. It has all 4 of these. Okay. Now there's a couple ways of doing this in ML. Data type rectangle is a rectangle of, now here's the constructor. See, it's a constructor of, but then notice that there's no names. Here I'm not using any names. I'm just saying it's a rectangle of 4 numbers. Real, 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 real. So it's, here I'm using a 4 tuple to represent these 4 numbers. Now I'm not giving them any names. This is one way to do it. I'm just saying, okay, there's a number here, a number here, and a number here, and a number here. And I will keep track of them myself. I'll think of this as X, Y, width, and height. Okay. This is not great because I'm not giving any names for them, but I do things like, here's a function, get X. See, I use a pattern matching. The function takes in a rectangle of X. I don't care what's here, what's here, what's here, and it returns X. So if you give me a rectangle, I can give you back the X field of the rectangle. If you give me a rectangle, I can give you the Y field of a rectangle. Notice I'm using pattern matching. Once I define my own rectangle, I can write patterns on my rectangle. So this is one of the neat things about ML is that patterns come from your types. They're not actually built into the language. The patterns that are in ML actually come from people defining types. Okay, so if I define a rectangle type, I now have a rectangle pattern. Okay, so here I can write my functions to do get X, get Y, get M, get here. Here I can do move. Okay, for example, if I want to move the rectangle, if you look in the Java version, that would mean updating X and Y. So this is going to take a new X, so it takes in a rectangle and the new X and new Y for the rectangle. And what it returns is a new rectangle with the new X and the new Y. Now notice that it doesn't, over here, this is kind of important. When you move an object in Java, you tend to mutate the object, but you don't have to write it that way. Normally, when we first teach people to Java, we teach them to write classes that mutate. But you could change this to be the following. In Java, you can make your rectangles immutable, and you could do this. You could say new return new rectangle, where it would be the X, Y, this dot width, this dot height. Okay. And now instead of being a void method, it would return a rectangle. And instead of mutating this rectangle, when you move a rectangle, you get back a new rectangle that is the moved rectangle. This is the immutable style of object-oriented programming, where you don't mutate objects, you return new objects that hold the, now strings work this way. Strings now, like when you say, when you tell a string to to uppercase itself, it does not change the letters in the string. It gives you back a new string with the uppercase letters in it. Okay. Now in ML, you almost always write things in the return a new object that holds you do not mutate objects in ML. It's actually hard to do that. In Java, it's more natural to mutate. It usually is considered an advanced idea to do this of don't mutate the object, return a new object with that is the moved rectangle. Okay. ML kind of switches things around. The natural way to do things in ML is I return a new rectangle where it's got the new X and the new Y and the old width and the old height. Okay. So the original rectangle, the input rectangle isn't modified. I get back a new rectangle that's been moved. Okay. Java, in ML, you could do it both ways, but ML makes it much harder to write the mutating version. In fact, I don't even remember the syntax for it because you usually don't want to write the mutating version of these things. Java makes it easy to do both. They're both pretty easy, but we tend to teach you the mutating version, and that's the way most people think that object-oriented programming is supposed to be, but the world's really changing its mind about that. Classic object-oriented programming where you mutate objects is starting to get less and less respected, and people are switching to a more, what you might call functional object-oriented programming, where when you move a rectangle, you get back a new rectangle that's the moved rectangle. Okay. Same with here. This one moved by, this would take the rectangle and move it. Like if this is +1, it would move the rectangle to the right 1 unit. So it's mutating, it's moving the rectangle by that amount. Okay. This would be one way to do it. That's the more old-fashioned way to do it. The newer way would be to return. Notice that there's no return value here. It's a void function. The more modern way is to return a new rectangle that holds the x plus delta x, y plus delta y, the old x, the old height, and the old width, or the old width and the old, okay? And then change this to return a rectangle. Okay, ML pretty much defaults to this style. Java doesn't actually have any preference. Java doesn't actually default to one style or another. It makes it pretty easy to write either style. In fact, I could have both of these in here. Now, this is kind of interesting from the point of view of Java. Suppose I try to do both of these. Okay. Okay. Notice I've got a move by. I can delete that. Okay. Move by, move by. Actually, let me put them next to each other. It's a little bit. So there's the two move bys. And then here's the two move twos. Okay. This won't compile. Does anybody know why this won't compile? They're not the same. Move by this much, return a rectangle, versus move by, move this much, and return void. This one, move to by that much, return rectangle, versus move to by that much to there, return void. But this won't compile. Why not? Java interview question. Are you ready for your Java interviews? Believe me, this is what they'll ask you. You know, this is the kind of stuff that you'll get asked. You know, this is very typical of modern interviewing. Ask questions like these. You know, so give it a stab. Does anybody see what's wrong with this? What's wrong with this?
The parameters are the same.
So,
It will confuse it, I think.
why? What's the rule? Java has overloaded functions. So I can have function, you know, Java has overloaded functions. I'm overloading. This one's got this with this, and this one's different. This with this. I'm overloading the functions. Why isn't this going to work? So you have to give me, so the answer's got to be real specific. I'm not sure, somebody wrote, the overloads have two types with same parameters. I'm not sure what you mean. The names of the parameters don't matter. It's the types that matter. So this is double, double. This is double, double. The fact that I use the same variable names doesn't matter. I could call this Bob and Alice, or I could just, you know, I could call this one DX and this one DY, and it'll still not compile. Okay. So here I use different variable names. This still won't compile. Well, why can't it? The compiler can't tell which function you're using. If I call move by, you know, if I'm using the return value, it's using this. If I'm using not using return value, it's using this. Yeah, you're getting it the right. The rule in Java is you cannot overload on the return type. You can only overload on the input parameters. Java does not allow overloading on the return type. So functions with the same name but different return type don't work. Okay, you can only overload on the input parameters, and it has to do with the, you know, like I say, it has to do with when you call it. It has trouble distinguishing between this thing and this thing using the return type. It's real hard to tell these apart using the return. Now it's easy to tell them apart here, but when you call them, it is a little tricky to tell whether you're calling this one or this one, because they'll have the same type of input, but they'll be using different returns. Okay, so the rule in Java is the way it would be, the right way to answer a question like this is you get, you know, overload with different return types. And the answer is no, you're not allowed to in Java. The compiler does not consider return type when differentiating overloaded methods. You have to overload on parameters, not on return type. Okay, so that's an important little thing about Java. Okay, you have to overload on parameters, not return types. Now, what would I do here? If I actually wanted these, I could do the following. I could say move by immutable. That's the immutable version. And then move to, there's the immutable. I'd have to give them different names. Okay, if I wanted both the mutating version and the non-mutating version, I'd have to come up with some kind of name. Move to immutable, move to, you know, okay. So now the thing important is that the language really makes it just as easy to write the mutating one as it makes it to write the non-mutating one. From the point of view of the language, the language doesn't have any preference whether you write mutating methods, mutating methods or non-mutating methods. The language itself is completely neutral about this. ML is not neutral about it. ML wants you to write the non-mutating version. It makes you jump through hoops to try to write the mutating version. And that's become, now ML designed the language that way. Java actually was designed with the mutating case in mind, actually. over time, people started realizing that there's really problems with the mutating case. It's falling out of favor, and the non-mutating case is becoming more prevalent. In fact, it was there all along. There's a reason why strings are immutable. If you play around with strings in Java, like if I just go over here to, where's my the visualizer? Yeah. When you do that, you're not changing S2. That drives introductory students crazy because Java's inconsistent about this. When is it that when you call a method, it actually mutates the object? And when is it when you call a method, it doesn't mutate the object? Well, on strings, this does not mutate the object. Boy. Oh. Okay. And you can see it. Call that method. See, nothing happened to S2 because it actually returned a new object. What you have to do is you have to say string S3 equal, and you have to capture the returned object. Okay. Oh, and the Java visualizer draws these things kind of funny. If you want to see them drawn the right way, you have to click this little box, show strings the right way. See, there's the return object. You have to capture it. If you don't capture the return object, it just gets garbage collected. Some methods in Java are designed to be mutating and some aren't. And notice that there's no way to know. This drives, it makes it hard to teach this stuff because you have to tell people, well, when you call some of these methods, it does one thing, and you call these other methods, it does a different thing. And how do you know which one it does? Well, you just have to remember. There's nothing in the language to hint that that's actually, that's not a mutating method call. It returns an object. Okay, so like over here, I probably did what would, I gave them names. I said, well, this one mutates, this one doesn't. Okay. Java has a lot of problems. We're learning how to write languages better. Java's way better than C and C++ in many ways, but Java still shows there's been 25 years of development in programming languages since Java was invented. But the funny thing is, ML is older than Java. And as languages get more and more sophisticated, they're getting more and more like ML. This is one of the big ironies of everything, is that ML is actually way older than Java. But as Java matures and as people develop new languages, they're actually going back to the ideas that ML pioneered in the 70s and 80s. Most of this stuff was developed in ML in the 80s. Java was developed in the first version of Java was 1995. Okay. And actually the version of ML we're using right now, I think, was 1998. So the current version of ML was actually slightly after Java, but the language, no, SML, Standard ML of New Jersey. When I think it's not, that's hard to read. What year the year this was finalized, I think, was in around 19. It doesn't even say that. Should look at the Wikipedia page. The current version was 2020, but those are 97. Okay, it's from 1997. Java's from 1995. But ML was a very mature, this version of ML is the current one we're using, but most of these ideas were developed in the 80s and in the early 90s. Okay. So it wasn't that this stuff came out after Java. Almost all these ideas were in ML in previous versions of ML. At this point, ML was pretty much fixed. At this point, they stopped developing it after 1997. Since then, it's been mostly bug fixes and things like that. Little minor changes. The language hasn't changed since 1997. So almost everything that was new in ML and interesting in ML was put there in the 80s. And so the Java people could have figured this stuff out. They could have actually, in a way, they could have figured out in 1995 that what they were doing was probably not really the right idea. But they stuck with what mostly the C++ people were doing, and they made Java more or less a better C++. Instead of making it like a better ML, they made it a better C++. And now they kind of regret it, because now over and over again, all the changes in Java in the last few years have been recouping ideas from ML. They just constantly keep recouping, drawing things out of ML. Like I say, the optional is an ML trying to get Java trying to get the algebraic data types. Okay. We'll look at some more of these examples on Thursday. This code is actually not that great. ML is not a perfect language. So in a lot of ways, this code is not really a lot better than Java. Okay. It's got advantages and disadvantages. In some ways, the code can be kind of cumbersome to work with. And I wrote another kind of rectangle here that uses, just show you, I'll put these up on the internet later, that uses type instead of data type. And I'm not even sure which is the preferred way. So there's type, there's data type and type. And so here's one way of defining a rectangle, and here's another way of defining a rectangle. So there ends up being two ways. I think this is the better way, and I think that's considered better than this way. And here I wrote move to, move by, grow to, grow by. Code's kind of ugly. The code here is a little bit better, but it's kind of weird. It's both, Java and ML are both kind of old languages. They both date to the 80s and 90s. So people are trying to come up with better and better ways to make these languages work. So ML has got a lot of things in it that Java doesn't, and Java is adopting things from ML. But if somebody was designing a brand new language, they wouldn't redesign ML either. Haskell's a little bit closer to what people would probably design, and some other languages. But ML is not the language people would write from scratch at this point. They would use a lot of ML ideas, but they wouldn't give you the language that's ML. ML shows its age in other ways. Java shows its age in some ways, and ML shows its age in other ways. So they're both showing their age, just that ML has so many things in it that Java doesn't have. Okay, so we'll play around with data types a little bit more on Thursday, and then we can, if there's any questions about some of the review material, you can ask questions about review material also. Okay. So anybody got any last second question? Okay, so we'll stop there. We'll put and say on Thursday we'll play a little bit more with data types and look at a little bit more about how ML manipulates, how it works with data types. So see you on Thursday. Bye bye.